Okay, so what we're doing today is talking about linear transformations. And this is, like everything else, very important. So let me, yeah, okay. And in the notes, this is chapter 3, section 3.1 to start in the latest set of notes. So we have vector spaces. Sorry, not 3.1. Let me get the right section. Yeah. Section 3.3. So we have vector spaces V and W and a function T from V to W. So T is called a linear transformation or a linear map, same thing, or a linear function, if it satisfies the following two properties. First, for all vectors V and V prime and V, if you take T of the sum of V plus V prime, that's like taking T of V and T of V prime separately and adding them up. And for all scalars, let's say reals, whatever the field is, if you take your vector and multiply it by the scalar C and take T of CV, that's the same as computing T of V and then multiplying it by C. So this is the fundamental definition. And there are lots of examples of linear transformations. So for example, you could have the identity map. From V to V, defined by I of a vector V is just the same vector V. So if you wanted to check that these two properties are satisfied, I of V plus V prime is just V plus V prime. But V is I of V and V prime is I of V prime. And similarly, I of C times V is CV, which is C times I of V. So this is kind of a trivial example, but it is an example of a linear transformation. What's another example? Well, the zero function. To find 0 of V to be the vector 0. So 0 of V plus V prime is 0, which is 0 plus 0, which is 0 of V plus 0 of V prime. And 0 of a constant times V is 0, but C times 0 is 0, so that's C times the 0 function applied to V. So these are kind of trivial examples. Here's a more interesting example. Suppose we take a function T from R2 to R2 and define it by T of xy is the vector 2x, 3y. So suppose V is xy and V prime is x prime, y prime. So if you add v plus v prime is x plus x prime, y plus y prime, and c times v is the vector cx, cy. So what is t of v plus v prime? Well, v plus v prime is this vector. That's t of the vector x plus x prime, y plus y prime. And what t does is it multiplies the x coordinate by 2, so 2x plus x prime, and it multiplies the second coordinate by 3. And this is the same as 2x plus 2x prime and 3y plus 3y prime, which is the sum of the vector 2x, 3y, and 2x prime, 3y prime. And this is t of v. That is, this is t applied to xy, and this is t applied to x prime, y prime, which is t of v plus t of v prime. And you can do the same thing with scalar multiplication. T of c times v is t of the vector cx, cy. That's the vector 2cx, 2cy, which is the same, 3cy, which is the same as c times the vector 2x, 3y, which is c times t of xy, or c times t of v. So the two necessary properties of a linear transformation are satisfied. And more generally, suppose we take a matrix A, which is A, B, C, D, and we define a function T sub A from R2 to R2 as follows. If V is the vector xy, then we define T sub A of V to be the matrix A times xy, which is A, B, C, D times xy. When you multiply, you get ax plus by, cx plus dy. And I claim that this is a linear transformation. But this actually follows directly from the fact that matrix multiplication is distributive. So if I had T sub A of V, T sub A of V plus V prime, that's the matrix A times the vector V plus V prime. But matrix multiplication is, this is AV plus AV prime, which is TA of V plus TA of V prime. If you want to do it in coordinates, you can also do it in coordinates. You would say T sub A of V plus V prime is the matrix A times, what is V plus V prime? X plus X prime, Y plus Y prime. So that's A, B, C, D times X plus X prime, Y plus Y prime. When you multiply the matrix times the vector, you get A times X plus X prime plus B X plus X prime. C times, plus BY plus Y prime. C times X plus X prime plus D times Y plus Y prime. That's just ordinary matrix multiplication. And you expand this, and you can write this as AX plus BY CX plus DY plus the vector AX prime plus BY prime CX prime plus DY prime. This is exactly A times XY plus A times X prime Y prime, which is T sub A of V plus T sub A of V prime. And you can check scalar multiplication in a similar way. So this is really an important example. And more generally, if A is an m by n matrix, then for every vector x in Rn, y equal ax is a vector in Rm. So we have a function t sub a from Rn to Rm defined by t sub a of the vector x is just the matrix A times x. And this is a linear transformation. What's another linear transformation? Let's go back to calculus. In calculus, you might have C01. This is the set of all continuous functions f from 0, 1 to the reals, right? 0, 1. Any function y equals f of x from 0 to 1 that's continuous is in this set. And in calculus, they tell you that the sum of two continuous functions is continuous and the product of continuous functions is continuous. So this is a vector space. And I want to define a function t from these continuous functions to the reals by integration. So t of the function f is going to be the integral from 0 to 1 of f of t dt. So this is a number, and the set of real numbers is a vector space. And this is linear, because in calculus you prove that t of f plus g, which is the integral from 0 to 1 of f of t plus g of t dt, the integral of the sum is the sum of the integrals. So t of f plus g is t of f plus t of g. And t of a scalar times f is the integral from 0 to 1 cf of t dt. And again, they teach you in calculus the integral of a number times a function. You can take the number outside the integral sign. So this is c t of f. So integration, this function, is a linear transformation from the vector space of continuous functions on the unit interval to the vector space of the real numbers. So that's very, very, very nice. Now, it's very important to know that composition of linear transformations is a linear transformation. So suppose we have vector spaces u, v, and w, and a function from v to w, t, and a function from u to v, s, and then you have the composite function, t composed with s. So the theorem says if s and t are linear transformations, then the composite function, t composed with s, is a linear transformation. And the proof goes as follows. So suppose I take two vectors in U, so that U and U prime be vectors in U. If I take T composed with S of U plus U prime, what does that mean? Composition of functions means this is T of U of S of U plus U prime. But S of U plus U prime, because S is linear, this is S of U plus S of U prime. And because T is linear, this is T of S of U plus T of S of U prime, which is TS of U plus TS of U prime. So the first requirement for a linear transformation is satisfied. The second is scalar multiplication. If I take T composed with S of the vector C times U, that's T of S of CU. That's T of S of CU is C S of U. And again, the C comes out, that's C T of S of U, which is C TS of U. So that, yeah, that's pretty good. Now, everything that you think about in terms of ordinary functions in calculus or advanced calculus, you can think about in the very special case, actually simpler case, of linear transformations. So suppose here is my vector space V, and here is my vector space W. If I have a set X, just a subset of V, T of X is just what we call the image of X. I'm sorry. It's the image of X under T. It's the set of all. So I have a linear transformation from V to W. It's just the set of all vectors in W of the form T of X, where X is in X. So I take this and I just look at everything. I send every vector in here over to W, and that set of the vectors is T of X. On the other hand, I can also take a set Y in W, and I can look at the inverse image. This is called the inverse image of Y under T. And this is all X in X, such that, sorry, all X in the vector space V, such that T of X is in Y. So it's everything over in V that gets mapped to Y. So I take a set Y over in W, and I look at everything in V that gets mapped into it. It could be empty, it could be nothing, but whatever it is. So whenever you have a function from one set to another, you always have this notion of the image of a subset and the inverse image of a subset. And the particularly important cases are when X is a subspace of V and or Y is a subspace of W. So Let me prove that. Let me just first make one sort of lemma. So we have a linear transformation from V to W. And the lemma says that if I take the 0 in V, I'll write it as subscript V, T of that vector is always the 0 over in W. So if I have 0 here and 0 here, 0 always gets mapped to 0. This is the 0 in the vector space V. This is the 0 in the vector space W. And the proof is very simple. It's based on the fact that 0 is equal to 0 plus 0. So T of 0 is T of 0 plus 0. Actually, I can give an easier proof. Scalar multiplication. 0 is the number 0 times the vector 0. This is because you take any vector and you multiply by 0 and you get the 0 vector. So T of the 0 vector is T of the scalar 0 times the 0 vector. This is a linear transformation, so the 0 comes out. That's 0 times T of the 0 vector. But 0 times any vector is the 0 vector, but T of 0 is over in W, so this is the 0 over in W. So that's a very short proof of that fact. So again, this is a lemma. T from V to W, a linear transformation. If V prime is a subspace of V, then the image T of V is a subspace of W. And if W prime is a subspace of W, then the inverse image is a subspace of V. And the proof is as follows. So this is 1 and this is 2. So the proof of the first statement is the following. So here I have V and W. Here I have a subset V prime. And over here I have the image T of V prime. And I want to show this is a subspace. So first of all, 0 is in V prime because V prime is a subspace, and a subspace always contains the 0 vector. So T of the 0 vector, which is the 0 in W, is in the image. So this image contains the 0 vector. Second, suppose that W1 and W2 are vectors in T of V prime. As I take 2 of V, I want to show W1 plus W2 is in T of V prime. I have to show that this set is closed under vector addition. But if W is in T of V prime, then there exists a vector V1 in V prime with T of V1 equal to W1. And similarly, if W2 is in the image of V prime, then there exists a V2 in V prime with T of V2 equal to W2. But if I have V1 and V prime and V2 and V prime is a subspace. So that means V1 plus V2 is in V prime, which means T of V1 plus V2, which is T of V1 plus T of V2, which is W1 plus W2 is in T of V prime. So this set is closed under vector addition. And similarly, if W1 is in T of V prime, and W1 is T of V1 for V prime, for V1 in capital V prime, and if I take a scalar C, V1 in V prime means CV1 is in V prime, because this is a subspace and it's closed under scalar multiplication. So T of CV1, which is CT of V1, which is CW1, is in T of V prime. So T of V prime is also closed under scalar multiplication, so it forms a subspace. So this proves the first half of the lemma. If you have a subspace of V and a linear transformation from V to W, the image of the subspace in V is a subspace in W. And the proof of the converse is similar. Again, we have V, W, and a linear transformation between them. And here we have a subspace W prime. And over here, we have its inverse image, F inverse of W prime. Right? F inverse of W prime is all the vectors V and V, such that T of V ends up in W prime. Ends up over here. So the first thing we observe is W prime is a subspace. So 0 is in W prime. And F of the 0 in V is the 0 in W. So the 0 in V is in F inverse of W prime. So 0 is there. So the 0 in V is in the inverse image. So this inverse image contains 0. Second, if V1 and V2 are in F inverse of W prime, that means that F of V1 is some vector W1 in W prime. F of V2 is a vector W2 in W prime. But W prime is a subspace. So that means W1 plus W2, which is F of V1 plus F of V2, sorry, T is my function, not F. So W1 plus W2 is T of V1 plus T of V2, which is T of V1 plus V2. W1 plus W2 is in W prime. So V1 plus V2 is in T inverse of W prime. So this T inverse of W prime is closed under vector addition. And finally, we have to show that this inverse image is closed under scalar multiplication, so that V be in F inverse of, T inverse of W prime. So that means T of V is W, some W in W prime, which means that T of C times V is CT of V is CW in W prime, so CV is in T inverse of W prime. So this subspace in W has, this inverse image in W in V is closed under scalar multiplication, closed under vector addition, contains 0, therefore it's a subspace. So, we've reached the point in this course that is, this is the beginning of the third week, which is analogous to the beginning of the third month in a regular semester, where basically everything we do is prove theorems about linear algebra. And there's a succession of very important theorems. But it's quick to do when you know what you're doing, but to understand it when you're seeing it for the first time, to understand it really takes a lot of work by yourself at home or wherever you study. Now, there are two very special subspaces that come up when you have a linear transformation. So here we have V, here we have W. These are my vector spaces. And I have a linear transformation from V to W. And in V, I have the 0, and in W, I have a 0 vector. So what is called the kernel of T, it's the set of all vectors V in V such that T of V is equal to 0. So 0 goes to 0, but you can have other vectors that go to 0. So of course, what this is, another way of saying this is the inverse image of the subspace in W consisting just of the 0 vector. The set just consisting of 0 is always a subspace. The inverse image of that subspace is what is called the kernel. So the kernel of T is automatically a subspace. Now, if you take any vector in V, it goes to some vector T of V in W, but it's not necessarily the case that every vector in W is the image of a vector in V. So you can look at all the images of vectors in V, and that's called the image of T. The image of T is all vectors W in W, such that W equals T of V for some V in the vector space. And this is exactly equal to T of V. V is a subspace of itself. T of V is everything that is in the image of V. So by the previous lemma, these are both subspaces. So let's just take an example to try and calculate these things. Suppose I take the matrix A equal to 1, 0, 0, 0, and let T sub A of a vector xy be A times xy. That's 1, 0, 0, 0 times xy. If I do matrix multiplication, that's the vector x0. So you can actually draw a picture of this, because in R2, if I take a vector xy, it gets mapped to x0. That means it's just projected straight down onto the x-axis. So this function from R2 to R2 it sends every vector to the x-axis. So xy gets sent to x0. But if you look at this in the just as an action within the plane, it takes a vector and projects it straight down or straight up to the x-axis. So what is the kernel of A? The kernel of A is all vectors xy such that t of xy is 0. That is the 0 vector. That's all vectors xy. What is t of xy? It's x0. So that's that t of x0 equals 0, 0. That just means x equals 0. That's all vectors of the form 0, y for any real number y. What is this? That's just the y-axis. So in the xy plane, the y-axis is the kernel of t. And you can see it just from the picture because this is 0, 0. What vectors project onto 0, 0? Just the vectors on the y-axis. What is the image of t? The image of t is all vectors, let's say uv, or x prime, y prime, where t of xy is x prime, y prime for some xy in R2. But this is just a set of all vectors x prime, y prime. What is t of xy? It's x comma 0. So it's all vectors of this form. That is, it's all vectors where the y coordinate is 0. It's all vectors x comma 0 for x and r. What is that? That's the x-axis. So the x-axis is the image of t. And again, you can see that directly from the picture because every vector under t is projected to the x-axis. So the image is just the x-axis. And the things which get projected to 0 are the y-axis. So the kernel is the y-axis. So that's a nice example. And let me just show this again. So I have t from R2 to R2 defined by t of xy is x0. So the kernel of t is the y-axis. That's the set of all multiples of 0, 1. And the image of t is the x-axis. That's all multiples of 1, 0. And notice the dimension of the kernel of t is 1. And the dimension of the image of t is 1. And the dimension of R2 is 2. And they teach you somewhere, and it's very important in linear algebra, that 2 is 1 plus 1, which is the dimension of the kernel of t, plus the dimension of the image of t. So that's a nice result. 1 plus 1 is 2. And this is a special case of another of the fundamental results in linear algebra, which I will prove now and prove again this afternoon, because it really is fundamentally important, and it's important to know. So the picture is always V, W, and a linear transformation. And over here, we have the kernel of T, and what is called, and the dimension, which is a subspace, so it has a dimension. The dimension of the kernel of T is always called, or is often called, the nullity of T. So the nullity of T, see, what is the kernel? Everything which gets sent to the zero, like to the null vector. So the nullity of T is the dimension of the kernel. Over here, we have the image of T, which is a subspace of W. So it has a dimension, and the dimension of the image of T is what is called the rank of T. And the fundamental theorem about linear transformations is the following. When you have this linear transformation T from V to W, if these are finite, if V is finite dimensional, the dimension of V is the dimension of the kernel plus the dimension of the image. It is equal to the nullity of T plus the rank of T. So if the dimension of V is finite. So if you have a finite dimensional vector space and a linear transformation from that vector space into another vector space, the dimension of the whole space is the dimension of the kernel plus the dimension of the image. It's the nullity plus the rank. And I'll show you a proof of this right now.
Wait, you said that the dimension is a finite, what was it? Like
So
the bottom left.
If V is a finite dimensional vector space, then every subspace is going to be finite dimensional, and the image is going to be finite dimensional. And the theorem says that the dimension of the kernel plus the dimension of the image is equal to the dimension of V. Right? Yeah, let me write it down again. So this is the theorem. So if we have V and W, this is only true for finite dimensional spaces. Finite dimensional vector spaces. I mean, a vector space can have infinite dimension, but we almost never consider that. And T from V to W, a linear transformation, then the theorem says that the dimension of V is equal to the nullity of T plus the kernel of T. This is the dimension of the kernel, sorry, the nullity of T plus the rank of T. This is the dimension of the kernel of T, and this is the dimension of the image of T. So let me give a proof. So here is V, and sitting inside of V, we have the kernel of T. So suppose the dimension of the kernel of T is K. So this is a K-dimensional subspace. So let V1 up to V sub K be a basis, that is a set of linearly independent and spanning vectors, let this be a basis for the kernel of T. And then extend, whenever you have a linearly independent subset of a vector space, you can add vectors to get a basis of the whole vector space. Extend to a basis V1 up to V sub K. Suppose the dimension of V is N. Vk plus 1 up to V sub N, which is a basis for the whole vector space V. And now let W be any vector in the image of T. So that means W is equal to T of V for some V in this vector space, right? I have some W in the image. That means there's some V that gets mapped to W. And because this is a basis for my vector space, V is some linear combination of the vectors in the basis. The C sub i's are scalars. So again, I have V is C1 V1, CK VK, CK plus 1, VK plus 1, up to CN VN. And T of V is this vector W. But what is T of V? T of V is T of C1 V1, is T of this whole thing. But because T is a linear transformation, this is C1 T of V1, CK T of VK, CK plus 1, T of VK plus 1, up to CN T of VN. So my W, which is T of V, is this. But these first K terms, these are all 0 because V1 up to VK are in the kernel. T of V1, T up to V, they're all the 0 vector. So W is in fact just equal to this. So what this says is every vector W in the image of T is a linear combination of the vectors Vk plus 1 up to V sub n. So this set of vectors, this spans the image of T. Now, I want to know what is the dimension of the image. I have n minus k vectors here. So the dimension of the image is at most n minus k. But I'm going to show that these vectors are linearly independent. So I claim Vk plus 1 up to Vn is linearly independent. Independent. I claim this is a linearly independent set of vectors. Well, suppose not. That means that, or suppose, let's just do it directly. that CK plus 1 VK plus 1 up to Cn Vn be equal to the 0 vector. So in that case, T of 0 is T of CK plus 1 VK plus 1 up to Cn Vn. T of 0, that's equal to 0. Because the 0 vector is always sent by a linear transformation to the 0 vector. So CK plus 1 VK plus 1 up to Cn Vn, if it gets sent to 0, it's in the kernel of T. And the kernel of T is spanned by the set V1 up to Vk. So CK plus 1 VK plus 1 up to Cn Vn is some linear combination of the first k vectors. If I rewrite that, I get minus, I'm just bringing this to the other side, minus C1 V1 minus CV2 up to minus CK VK plus CK plus 1 VK plus 1 up to Cn Vn is the 0 vector. So this is a linear combination of the first n vectors. And actually, the n vectors in my base is equal to 0. But V1 up to Vn, this is a linearly independent set. So all of the CIs are equal to 0. So in particular, let me just go back and repeat this a little bit from the beginning to make it a little bit clearer. So V1 up to Vk is the basis for the kernel of the transformation. I extend it to a basis for the whole vector space. If I take any vector W in the image, it's T of V. That means it's T of some linear combination. Because T is a linear transformation, I can write this as this linear combination of vectors. T of V1 up to T of Vk, they're all 0. So W is CK plus 1, T of Vk plus 1 up to Cn T of Vn. So what that says is that every vector W in the image of T is a linear combination of T of Vk plus 1 up to T of Vn. So these n minus k vectors, should have a T here, these n minus k vectors span the image. And I want to prove that these n minus k vectors are linearly independent. So let me do it a little bit more carefully. So suppose some linear combination of these n minus k vectors is 0. But because of the linearity of this function t, this is the same as t of ck plus 1 vk plus 1 up to Cn Vn, which means this vector is in the kernel of T. So this vector has to be a linear combination of the vectors in the basis for the kernel, C1, V1 up to Vk. So I have this relation. If I bring this over to the other side, minus C1V1 minus CKVK plus CK plus 1 VK plus 1 up to CNVN is 0. But these n vectors are linearly independent. So it implies all of these coefficients have to be 0. In particular, CK plus 1 up to Cn are 0. Which means that the vectors T of Vk plus 1 up to T of Vn, that set of vectors, this is linearly independent. And it also spans the image of T. So the dimension of the image of T, which is the rank, is n minus k. And the dimension of the kernel of T is k. So the nullity of T plus the rank of T, that's k plus n minus k, is n, which is the dimension of V. That is the fundamental theorem about a linear transformation in linear algebra. So this is worth the investment of a great deal of time to understand. And I'll talk about this theorem again this afternoon. I'll prove it this afternoon, and I'll give several examples this afternoon. But it is discussed at length in section 3.3 of the new set of lecture notes that I put on Blackboard yesterday. Okay, so there's a lot to learn here. So there are new definitions, new concepts, and new results. That's the story. Okay. Any questions about this before we stop for the morning?
Well, not about this particular. I was wondering, like, you know, exam 2 is just like in 2 days. I was wondering if we were going to have like a review for a review sheet like exam 1.
Yeah, I will have a review sheet. I'll put it together tonight and go over it tomorrow.
Okay, thank you.
Yeah, okay. Okay, that's it for right now then. Bye all.